Hello everyone, hope you all are doing great. Today we will be exploring the topic of electric double layer where I will take you through my work of modeling the effect of a variable dielectric within the electric double layer to see how it changes the profiles such as concentration, potential within this layer. My name is Vivswan and I'm working under Professor Anand in the AGR lab. So let's start today's presentation. Whenever we have a charged surface in contact with an electrolyte, there will be a formation of a double layer. Take for example this surface. Around this negatively charged surface, we will have a surface of positive charges. This layer, quite immobile, is known as the Stern layer. Moving on from the Stern layer, we will have diffuse layers in which we can find positive and negative charges whose concentration gradually reduces as we move towards the bulk. The concept of EDL has always been fascinating to the researchers because of its application in various areas. Say for example supercapacitors. These devices store majority of their charges in this double layer and not in the bulk. Or the formation of electric double layer at the interface of solution and ion exchange membrane. Or in the colloidal studies wherein the stability of the colloids are dependent upon the formation of the electric double layer. To get a model for this electric double layer, Helmholtz first conceptualized the idea of a single molecular layer of counterions balancing the surface charges. Boyle-Chapman later came up with the idea of a diffuse layers of positive and negative ion whose concentration gradually reduced as we move towards the bulk. Stern improved this model by saying that ions do have a finite charge and they cannot come closer to a certain distance a from the charged surface. Plus, he also conceptualized the idea of the adsorption of counterions to the surface, the layer being came to known as the Stern layer, and after which there is a start of a diffuse double layer. In the recent years, researchers have added more things such as Gupta Stone and added the valence asymmetricity concept, the steric concept, and the dielectric decrement. Cial et al. Improved upon their model by addition of the van der Waal interactions, the wall and the soft repulsions. So my work is based on what Anirudh Cial et al. Has done, and I have to fill these research gaps to come up with a better model for the electric double layer. So to find the potential and the concentrations of the ions within the EDL, we start with the Helmholtz free energy equation. We differentiate it to get the chemical potentials. We apply the boundary conditions, non-dimensionalize the parameters, use the most famous Poisson Boltzmann equation to solve it. We write it in the MATLAB accepted form as a function of ODEs. We solve using MATLAB to get psi values, and then we put back these psi values to get n positive and n negative values. Here, the point to note is that n positive and n negative are the solely function of psi, and these are all the dimensionalized parameters that are used in my equation. So these are all the changes that we get upon the inclusion of variable dielectric. The point to note here is that both n positive and n negative are higher order transcendental functions of psi, d psi dx, and n positive and n negative. To go with our normal procedure to solve this problem, we would first have to write it as a system of first order differential equations, but the problem here was that n and n minus were a function of y1, y2 as well as n positive and n negative. A situation arises that can we separate n positive and n negative? Analytically, we can't, and hence we end up in a loop, but numerically, we can, and this is what I found in my research. I use an fsolve function in MATLAB to solve this problem. I first call the BPP5C function, which uses the Runge-Kutta method to solve the set of differential equations. And within the ODE function, whose work is to frame these differential equations, I call these fsolve function, which gave me the n positive and n negative values for the given y1, y2 values, and these were used to find y1, y2 values at each and every mesh point. So let's discuss the results for two different kinds of electrolytes. Upon the inclusion of a variable dielectric into the system, we observe a less rapid decrease in the potential values for both the cases. The reason for this is that near the charged surface there is a high concentration of counterions. And due to this high concentration of counterions, there is a further decrease in the dielectric constant. And a decrease in the dielectric constant is proportional to the charge holding capacity of the system. So these things lead to the saturation of the counterions in the vicinity of the electrode, and hence the decrease in the potential is not that great. In fact, it is also been shown by these black lines that the linear region is quite uh, long as compared to the green, as compared to that in the green and the red curves. Okay, so talking about the cation concentrations, we see a similar nature of the graph but with the lower peaks. We observe a sudden jump in the concentration near to the electrode surface for NaCl because sodium being a small ion, here the van der Waals forces of attraction are comparable to the electrostatic forces of repulsion, which indeed is not a case for the magnesium ions. For the magnesium ions, their high size as well as the dielectric decrement is the reason for a negligible amount of magnesium ion present even up to a significant distance from the electrodes. Now we've moved to the negative ions. We again see a similar nature in the graph, but again the peaks are a bit lower, and this amounts to the fact that there are lesser concentration of negative ions and as well as the positive ions in the electric double layer. Okay, so upon the addition of a variable dielectric, I came to the conclusion that the decrease in the psi values was observed to be less rapid, as well as the concentration profiles for the positive and the negative ions was found to exhibit the similar nature in the graphs, but with a reduced concentration and the peak values. I will be continuing this work forward with an answer wherein I'll be considering the change in electrolyte polarizability, the concepts like excluded volume interactions, and I will be also finding out the double hump nature of the capacitance in the near future. At last, I would especially like to thank Anand sir for believing in me, motivating me, and guiding me throughout my research work. Anirudh Bhaiya and Utkarsh Bhaiya for helping me to start at the beginning and upon whose work I built on my research. Piyush Bhaiya and Shivam Bhaiya for helping me out to finish up my presentations, and my fellow intern Balaji for helping me and being with me at the beginning, and to the entire AGR group for clearing very small doubts and helping me out in every matter, and at the last to IISc as well for giving me this opportunity to intern as the best institution of India. And thank you to all for being such a patient listener. Thank you.